So there is no electricity at my place, and that's why I won't be able to switch on my camera. Okay, let me start. Let me see if my mic is on. Yeah, it is on. And so my name is Shubham Rai, and I'm a PhD research scholar in Department of Applied Mechanics, IIT Delhi. So today we'll start with week 12. So let me just write. Firstly, we will recapitulate what you have studied in week 12, and then we will move to some problems. Okay, just wait a minute. Okay, so do you remember what you had studied in week 12 lectures? Are you able to recall? Okay, so if you're not able to, let me write this for you. So in week 12, you would have studied related to theory of failures, right? And how many theory of failures you have studied? Can you tell me? So theory of failures that you would have studied are, so first one was maximum principal stress theory. It says that the failure will happen in the material when maximum principal stress will exceed the yield stress of the material, right? So we can write that maximum of x and lambda 1. So lambda 1, we are saying that lambda 1 is the value of maximum value of the principal stress, right? And maximize over x means we are maximizing over all the points in x, all the points in the body, and that maximum should be less than the yield stress. So if at any point in the body maximum principal stress exceeds yield stress, the failure will happen. Now the second one was maximum shear stress theory. Similarly, the shear stress at any point should not exceed the shear strength of the material, right? And how do you determine shear strength? It is usually half of the yield stress when we do a uniaxial tensile test. So yield stress, if yield stress is sigma y, then maximum, then at that yield stress, or at that amount of yield stress, maximum shear stress will be sigma y by 2. So we can say that, let's say we have principal stress lambda 1 and lambda 2 here, and then divide by 2. So this will be the shear stress that you will have in the body. And this is you'll have to find the maximum among. So let's say you have three principals as lambda 1, lambda 2, lambda 3, and we are assuming that lambda 1 minus lambda 3 is maximum among lambda 1 minus lambda 2 minus lambda 3, and lambda 1 minus lambda 3. So this is your maximum shear stress, and that should be less than maximum shear stress obtained from the uniaxial tensile test, which is sigma y by 2. So this is the sigma y, you already know that it is yield stress in tension. So we can say that sigma y is yield stress in tension, and lambda 1 comma lambda 3 are maximum and minimum. Principal stress values. Okay. Now you have, let's say you do not do tensile test, rather if you do a torsion test, pure torsion test, then you will directly get the maximum shear stress at the material will fail, at stress at which shear stress at which the material will fail. So you directly get that from the pure torsion test, because uh, that will be subjected to pure shear. Specimen will be subjected to pure shear in that case. So let's say that shear strength is tau y, and so this will be determined from the torque that you will be applying on the specimen, and the radius of the specimen divided by polar moment of area of the specimen, right? So now you have one more theory, which is distortional energy theory. So let me write that as well. Yeah. So distortional energy is the energy um, which is spent in distorting the body, that is changing the shape of the body. So we can say that it is distortional energy theory. So we say that distortional energy, so that is equal to total energy minus volumetric strain energy. So it means from the total strain energy you are subtracting volumetric strain energy. So now the strain energy that will be left will be responsible for changing the shape of the body. It will not change the volume of the body. Okay, and you can imagine that distortion energy theory is mainly valid for ductile materials. So in ductile materials, you can imagine that when the shape of the body will change, or the body will get distorted, and then only there will be failure, because there will be huge, I mean, I'm just saying in a very vague language, but there will be huge movement and displacement of the material during distortion. So that may lead to failure. Anyway, so exact reason why distortion energy theory leads to failure in ductile materials. So for that you need to study material science, and you'll have to go at the granular level and study the dislocation moment and moment of grain boundaries. So now, so we say that let's firstly write down what is strain energy per unit volume. So if you remember, the expression for strain energy per unit volume is nothing but 1 over 2e, and then in terms of principal stresses I'm writing, so it is sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu. Nu is the Poisson's ratio. Sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Okay, now you have volumetric strain energy. So if I write here only volumetric strain energy, so that will be equal to 1 over 6e, and that is sigma 1 plus sigma 2 plus sigma 3 to the whole square, and then you have 1 minus 2 nu here. Okay, so there is one very important conclusion we can draw from here. So let's see, let me write this in this form. So when Poisson ratio here is 0.5, this term will go to 0 and whole term will go to 0. It means volumetric strain energy will be 0. It means volume of the material will not change, and such materials are incompressible materials. So when this is the isotropic material that we are dealing with. So in isotropic materials, when Poisson ratio is reached 0.5, so um, the material becomes incompressible. Okay, and you might be thinking that a very hard material should be incompressible material, but it is not like that. Actually, the materials like rubber are incompressible materials because although they are very easy to deform rubber, but if you deform from one side, it get inflated from other side. But let's say if you do not allow it to inflate from any side, and you try to deform it by applying hydrostatic pressure from all sides, then it will be very difficult to deform rubber. In that way, it is um, incompressible, near to incompressible material. Whereas the materials like steel, those are compressible because their Poisson ratio is not zero point 0.5 or near to zero point 0.5. Okay, and then there can be, from here you can, from this volumetric strain energy formula, you can also see that this Poisson ratio can have negative values as well. So there are materials. So can you imagine of a material where Poisson ratio is negative means you are stretching a material and the transverse side of the material is also getting extended. So um, there you have negative value of Poisson ratio, right? So those kind of materials are there where you have negative value of Poisson ratio, because Poisson ratio is usually defined as negative of longitudinal, negative of transverse strain over longitudinal strain. So um, so if a Poisson ratio is negative, so longitudinal strain will become a transverse strain will become positive. So your muscles, actually human muscles are one kind of material. So human muscles are, we can say, have negative Poisson ratio. So if you stretch your muscles, they get in the transverse direction, their dimension will increase. Also, there is one more kind of material known as auxetic structures, which are made of honeycomb shaped unit cells. So those honeycomb shaped unit cells, if you stretch those honeycomb shaped unit cells in one direction, so transverse to that direction, they will get extended, not compressed. Okay, so two kind of materials have negative Poisson ratio. I mean, there are many materials, but I have given two examples. One is human muscle, and then second one is auxetic materials. So, and they have a lot of application actually uh, in high strain rate regime. So let's say a bullet is striking on some structure. So, and if that structure has a negative Poisson ratio, means the bullet will try to compress the material, and then the transverse direction dimension will also increase in that case. Sorry, I think I'm sorry. So when bullet will try to compress the material, so transverse direction will also get compressed, and the density of the material thus will at a particular material point will increase, and this will lead to um, bullet should have then higher energy so that the material fails. Okay, so if the bullet will have lower energy, it will not be able to easily rupture the materials with negative Poisson ratio. Anyway, so let me go to the next one. So I have written volumetric strain energy. Now I should write distortion energy. So if you write distortion energies, that will be one plus nu by 3e into sigma y square. That is distortion energy, and then you have critical distortion energy. Sorry, this is critical distortion energy. Let me write firstly the generalized expression, then I'll write expression of critical distortion energy. So generalized expression, in terms of principal stresses, distortion energy is 1 plus nu by 3e, right? And you have sigma 1 square, sigma 2 square, sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma. So that's what you have. And then you have critical distortion energy. So critical distortion energy is the energy consumed, energy per unit volume that has been consumed in uniaxial tension test. So since this is energy per unit volume, so it doesn't matter. So we are taking critical distortion energy from uniaxial test because it is energy per unit volume. So we can take from any test and apply it to three-dimensional conditions as well. Since we are taking from uniaxial test, so the energy will be, so only sigma y will be present, that is at the failure point the stress will be equal to yield stress, and let's say sigma 1 will be equal to sigma y and sigma 2 sigma 3 will be 0. So this expression will lead to 1 plus nu by 3e and sigma y to the whole square. Okay, and so distortion energy, maximum distortion energy theory says that distortion energy per unit volume in a material should be less than equal to critical distortion energy per unit volume. That means this distortion energy formula, which is 1 plus nu by 3e, and we have sigma 1 square and sigma 2 square and sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. So that should be less than 1 plus nu by 3e and sigma y square. Okay, so that's it, I think. So now you have, I'm just simplifying, so I think 3 will get cancelled, so 3 won't come here. Yeah, And 1 plus nu by 3, I mean this whole thing will get cancelled. So finally you have this theory. Sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 3 minus. So that should be less than sigma y square. Okay, so this is finally we have this maximum distortion energy theory. And then we have, you would have read about thermoelasticity. That is the effect of temperature on the material. So, so thermal strain that would be developed due to temperature effect will be, that will be epsilon t, so that should be equal to alpha delta t, where delta t is the change in temperature and alpha is coefficient of thermal expansion. Right, so and the strains that will be there for considering this thermoelasticity or thermal strain, so strain in x direction will be 1 over e and sigma xx minus nu times sigma yy plus sigma zz. Apart from this strain due to stresses, there will be additional strain due to temperature, so that will be plus alpha delta t. Similarly, this is 1 over e and we have sigma yy minus nu times sigma xx plus sigma zz plus alpha delta t, right? And then you have epsilon zz, then 1 over e, and then you have sigma zz here minus nu times sigma xx plus sigma yy. So finally you have these strains considering the effect of thermoelasticity. Now coming on to the problem, so let me write down the first problem. The first problem says a cylindrical tank is made of steel for which ultimate tensile strength is 150 megapascal and the pressure inside the cylinder is to be 1.3 megapascal. Okay, now using theories of maximum principal stress, maximum shearing strain, shearing stress, and distortion energy, find the thickness of the cylinder if diameter of the cylinder is so there are various diameters. So let's say you have 1.5 meter as the diameter, 1 meter as the diameter, and zero point 0.5 meter as the diameter. So we will consider the cylinder to be a thin cylinder and we'll apply all the formulas of thin cylinders to it. So and you also have to use a factor of safety of 5. Okay, so factor of safety of 5 means you have to reduce the maximum yield stress or shear stress by factor of 5, or whatever failure index that you are taking, so you have to reduce that index by a factor of 5. Okay, so can you try to solve this question? Yes. Okay, so let me give you a solution. So what will be the hoop stress in this cylinder? So formula is PD by 2T. If you remember, for thin cylinders, the formula for hoop stress is PD by 2T, which is so 1.3 megapascal is the pressure, and diameter we do not know. I mean, we know, but we will insert it later. So let and 2T, right? So this is hoop stress, and what will be longitudinal stress? So this will be in megapascals because pressure is in megapascals. So longitudinal stress is PD by 40, so that will be 1.3 D divided by 40, right? Now you have, let's say, tau max. Okay, so maximum shear stress here you have. So what will be maximum shear stress? So that will be we want to find out maximum shear stress actually. So since these two are normal stresses, and in radial direction in thin cylinders, we assume that sigma r is 0. So the maximum shear stress, if we consider the theta r plane, so theta in theta direction there will be hoop stress, and in radial direction there will be zero stress. So maximum stress will be this one, maximum principal stress will be this one, and minimum principal stress will be 0. So that's why maximum shear stress will be maximum minus minimum principal stress is divided by 2. So maximum is 1.3d divided by 2t and minus 0 divided by 2. So you will get 1.3d divided by 4t. Right. So then one more observation here, that sigma. So let me draw some more circle. So in this theta z plane. So what I'm assuming is, let's say you have the cylinder. So let's say this is z direction, and in the cross section of the cylinder we have theta and r direction. So here we have, let me take the coordinates somewhere else. Let's say you have a cylinder like this. So let's say here you have coordinates. So let's say this is z direction, and this will be theta direction, and this will be r direction, right? So these three will be perpendicular to each other, okay, at a particular point. So this sigma, so sigma h and sigma l, so this will be in theta direction of hoop stress, and sigma l will be in z direction. So if you draw element here like this, let's say if you draw element, small element here, right? So your this will be your sigma l, right? And this will be your sigma theta, sigma h hoop stress. You also can write sigma theta. And now if you draw more circle based on this, so and both are of same sign because pressure is, so both are PD by 2T, PD by 2T, both will be positive. So both are of same sign, so they will lie somewhere here. So let's say this is sigma h and this is sigma l. So we will get more circles, something like this, right? So this is, let's say this is sigma h and this is sigma l. What I want to say is now if you try to find out maximum shear stress, maximum shear stress, so we'll have to go for theta r plane for finding maximum shear stress. So maximum shear stress will be sigma l divided by 2, because um, this is corresponding to rz plane, right? Yeah, not rz but theta z plane. Yeah, so this is corresponding to theta z plane, but you have to, maximum shear stress will not happen in theta z plane. It will be, you have to take rz plane. So because sigma r is 0, sigma z is, sorry, r theta plane. Yeah, so if you take r theta plane, so that will be sigma h, and so principal stresses will be in r direction, it will be 0, and in theta direction it is sigma h. So maximum shear stress in that case will be sigma h divided by 2. That's what we have written here. Now if we consider yield stress, so since both, okay, and now you also know that tau max will be yield stress divided by 2, right? This you already know in uniaxial tensile test. From uniaxial tensile test, this will be the case. So it will be yield stress divided by 2. And this should be equal to um, sigma hoop stress divided by 2, right? If we want to apply maximum shear stress theory. I mean, this should be obviously greater than sigma hoop stress divided by 2. This is what this tau max is, sigma hoop stress divided by 2. And if you, so this is as per maximum shear stress theory. Now let's apply maximum yield stress theory. So maximum yield stress theory, or maximum, sorry, principal stress theory. So if you apply maximum principal stress theory, so for that case, your lambda 1, that is maximum principal stress, that will be equal to sigma h, right? And that should be less than sigma yield. So essentially, so this is as per maximum principal stress theory, right? Now these two theories are same actually here, because when your stresses have the same sign only two such stresses are present here, and when those stresses have the same sign, then maximum shear stress theory and maximum principal stress theory is the same result. This also is sigma h is less than equal to sigma less than sigma y, and this is also sigma h less than sigma y. So if they would have some different signs, then tau max would not have sigma h would not have been sigma h by 2. It would have been something like sigma h minus sigma l, because then sigma l would have been positive, then minus minus would have been I mean sigma l would have been negative, or sigma h would have been positive. So if you do sigma h minus sigma l, so that will be essentially addition of two values, because sigma h is positive and minus of sigma l is a negative, minus of minus will be plus. So you get a value higher than sigma h by 2, right? So in that case, your shear stress would not have been would not have been just sigma h by 2. But since they both have same sign, so your maximum shear stress will also be sigma h by 2. So here we can say that so what we can conclude is, since sigma h and sigma l both are positive, so maximum shear stress and maximum principal stress theory will be same. Are same. So now here you have sigma L is equal to sigma Y. Um, sorry, sigma H actually. So if I let me write sigma Y. So sigma Y will be ultimate tensile strength divided by factor of safety. So ultimate tensile strength given to you is here, you can see. So it's given here. So it is 150 megapascal, and factor of safety here is 5. So you get 30 megapascal, right? So this is the allowable yield stress, and then you have, as per maximum principal stress theory or maximum shear stress theory, you should have sigma h less than sigma y. So sigma h is how much? 1.3 divided by 2t. So that should be less than 30. So let's suppose we take the maximum value. So we are left with 1.3 d 2t equal to 30. Let's say we take the maximum value. So d will be, t will be t thickness. You need to find d is already given to you. Thickness will be 1.3 d by 60, right? So this will be the thickness. So from here we can say that first part is, for d is equal to 1.5 meter, we'll have to convert meter into mm. So let's say we want in mm, thickness in mm. So thickness will be 1.3 times 1500 divided by 60. So if you calculate, so it will be 32.5 mm. For the second case, for now you had three cases of d is 1.5, d is 1, and d is 0.5. For the second case, d is 1 meter, that is 1000 mm. So t will be how much? 1.3 multiplied by 1000 divided by 60. So if you do that, so finally you will get 21.7 mm. And for the third case, your d was 0.5 meter, which is 500 mm. And if you now solve, t is equal to 1.3 multiplied by 500 divided by 60. So finally you will get 10.8. Okay, so this is as per maximum principal stress and maximum shear stress theory, and both of them will leave same result because hoop stress and longitudinal stress have the same sign. Now going for maximum, you going for distortional energy theory. So if you use distortional energy theory, if you use that. So since you have only sigma 1 sigma 2, like sigma 1 we can take as, let's say, take sigma 1, that is first principal stress, as hoop stress, and second principal stress as longitudinal stress, and third principal stress will be 0, because in our direction we don't have any normal stress in thin cylinders, we are assuming it to be 0. So now if you apply in maximum distortion energy theory, so you will be left with sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So that should be, I'm taking the maximum case, although it should be less than, but I'm taking the maximum case, so that should be equal to sigma y square. Now if you put the values, so sigma 1 is sigma hoop stress, which is 1.3d divided by 2t to the whole square, plus sigma 2 is nothing but 1.3d divided by 4d, right, to the whole square, minus multiplication of these two, sigma 1.3d divided by 2t times 1.4d 1.3d divided by 4t. So that should be equal to sigma y square, right? Now, so actually you can bring sigma y to the left hand side and take t to the right hand side. So if you take 1.3d over 2, and sigma y will also come here. So this, if you take common, let's say, so here in the first term you will be left with 1. In the second term you will be left with 1 over 2 whole square, that is 1 over 4. And in the third term, so it's really plus, and in the third term you will be left with you've taken 1 over 4, so you've taken 1.3d common, and then sigma y common, and 4 you have taken common, so you'll be left with 2. Oops, sorry. So that should be equal to t square. Okay, now if you solve this, so finally you should get 0.317, and this will be d divided by 30 and to the whole square. So sigma e will be 30, and this is t square. So finally you can put the value of d. So for d is equal to 1.5 meter, that is 1500 mm, your t should be equal to 28.15 mm. You just put in this formula here. Okay, and for d is equal to 1.0 meter, you have 1000 mm of d. So thickness that you will get will be 18.77 mm, and for d is equal to 0.5 meter, you have 500 mm. Thickness that you will get is 9.40 mm. Okay, now you have problem 2. So in problem 2, so a solid circular shaft is subjected to a bending moment of 3 kilonewton meter and a torque of 1 kilonewton meter. So here you both have bending moment and torque in the circular shaft, and the shaft is to be made in carbon steel for which sigma y is 480 megapascal and tau y, how much will be tau y? So tau y should be um, half of this, right? So half of this will be how much? Actually, it will not be half. To be exact, it will not be half. It will be, I think, 480 divided by root 2. So the half is as per maximum principal stress theory, right? So as per maximum principal stress theory, yield stress um, from the uniaxial tensile test, actually, you get maximum shear stress to be sigma y divided by 2. But here it will be tau y is given to you, which is 265 megapascal. Okay, so it's not exactly half. Okay, it may be. So if you apply distortion energy theory, no? So let's see here. So let's say that um, so maximum distortion energy is this one. When you apply, when you're doing the axial tensile test, and when you do a torsion test, okay. So in that you will have some pure. It will be a case of pure shear, and you will observe that the normal stresses will be equal to shear stresses in that case, and so sigma 1 will be equal to tau, and sigma 2 will also be equal to tau in this case, in that case, and sigma 3 will be 0. So if you take that way, so this will be um, so here you have to put, so tau square plus tau square is 0, so it will be 2 tau square, and sigma 3 is 0, so these two terms will go away, and here you have, so you will be left with 1 tau square. It comes actually root 2, so let me see. So if you make let's say pure shear, so you have this here. So okay, so yeah, so one is tau and one is minus tau. So if you put here, so you'll get tau square plus tau square, and this is also plus tau square, so you get 3 tau square. And that should be equal to sigma y, so your sigma y should be equal to square root of, if you compare um, cannot compare like this, so compare the distortion energy, so that should be root 3 times. Let me just check. Yeah, so I think it's root 3 times. So 480 divided by root 3 comes out to be 277 approximately. So I think it's derived from there. So what I have done is, if you do a pure torsion test and uniaxial tensile test and compare the distortion energy of both these two configurations. So in uniaxial tensile test, you will have this as the critical distortion energy, and This is the critical distortion energy. And in torsion test, then that is pure torsion. So here um, you have shear stress only, and normal stresses will be zero in that direction. So we get this kind of Mohr circle, and then one normal stress, one principal stress is positive, one other is negative, and both have same magnitude as that of shear stress, because this is equal to radius of the circle. If you put it here now, sigma 1, sigma 2, so you will get three tau here. Finally, the tau that you will get will be sigma y square should be equal to 3 times tau square. So if you take square root, so sigma y will be equal to 1.732 times shear strength. Okay, so that's how it's been done. But the here you get, here we have written that your maximum principal stress theory, so that is equal to sigma y by 2, because sorry, maximum shear stress theory. So one shear stress that you can get is from uniaxial test. So in uniaxial test, your maximum shear stress is we can say that sigma y by 2. So you can compare your maximum shear stress in a material in any configuration in subjected to three-dimensional state of stress to this maximum shear stress obtained from uniaxial test, and then you can also obtain a maximum shear stress directly here. So from the torsion test, and that value is tau y. You can compare from there as well. Okay, so these two values may be different. The tau y need not to be exactly sigma y by 2 always. So if you are taking maximum, so suppose you have not done this torsion experiment, so you can use this formula. But if you have done torsion experiment, you have the value of shear strength, so you should use this formula. Okay, because if you will do a pure torsion test, so your principal stresses in that case will be tau and minus tau. Okay, so we will move to the next question. So you have yield stress and shear strength of the material, and shear strength is not exactly half, because half of this is 240. Okay, but it is 265. It's more than half. So if the beginning of plastics deformation is to be avoided, means you have to take yield stress as the failure stress. So you have to calculate the shaft diameter using, first is maximum principal stress theory, second is maximum shear stress theory, and third is distortion energy theory. Okay, so let me let me draw the shaft. Okay, so here you have a solid circular shaft. It is subjected to bending moment and torque both. So you draw the shaft. So let's say shaft is like this. Okay. So now this is, I'm assuming that this is the x-axis, and here you have applied a bending moment and torque both. So this is x-axis, and let's say here you have applied a bending moment, and then here you have applied the torque. You do torque and as naming the torque as empty. Okay, maybe just representing it like this. Maybe it's okay. So uh, let's say that D is diameter of shaft, and we know that M was bending moment is 3 kilonewton meter, and torque that you have applied is 1 kilonewton meter. So we can calculate equivalent bending moment. So equivalent bending moment will be, so do you remember the formula for equivalent bending moment? It comes from a derivation. You can derive it from using Mohr circle. So equivalent bending moment is ME, which is given by 1 by 2 times M plus square root of M square plus MT square, or you have minus also half of M minus, because you have two principal stresses. Let me connect to my Wi-Fi because now the electricity has come. So just wait a minute. Okay, so I think now, are you able to hear me? Okay, so let me start. So here you have equivalent bending moment. Let me see if recording is going on. Yes, it is going on. So now if I just calculate, so it is m is 3 and mt is 1, so it will be 3 plus 3 square plus 1 square, or 3 minus 3 square plus 1 square. So finally here you either you get, so what will be the, so can you calculate? So that will be square root of 10, and so that will be 3.08 actually, kilonewton meter, or so this will be square root of 10 plus 3 and divided by 2. So that should be 0.08 kilonewton meter, right? 3 minus square root of 10. And this should be minus actually. Okay. So this is equivalent bending moment that you have obtained, and we just, so what will be the maximum principal stress? The principal stress from this equivalent bending moment will be m into y by I. So me y will be equal to d because that is the maximum distance, and um, I will be how much? So we can say that it is pi d4 by 64 divided by 2. Okay. So now can you calculate? So finally we will have this 32 me by pi d cube. So because y will be d by 2, that's what I have written here. So y will be equal to radius because that is the maximum distance from the center. So that's what I have written here, and I will be pi d4 by 64. Finally you will get this. So if you put all the values in this formula, so 32 into 3.08 times 10 times 10 is power 3 because it is kilonewton meter and divided by pi d cube. So finally, approximately you will get 31 into 10 is power 3 divided by d cube. Let me just check. I mean, you will get this only, but wait. Yeah, approximately it is. I've just written approximate value, so you should get something somewhere around this. And sigma 2 will be minus because ME is minus 32 into 0.08 into 10 to the power 3 divided by pi d cube, right? So finally, let me see what we are getting, what we will get here. So 32 into 1000 2.08 divided by 814. So approximately you will get minus of 0.81 into 10 to the power 3 divided by d square, d cube, and the unit is obviously Newton per meter square here also. Okay, so these are the maximum and minimum principal stresses that you are getting. So, and then we can find equivalent torque also. So equivalent torque is this part, m square plus mt square, square root of that. So mt equivalent, I'm just writing here, that will be m square plus mt square. So that should be 9 plus 1, which is 3.08 into square root of 10, right? So that is not 3.0, that is 3.16. That should be 3.16 into 10 is power 3 Newton meter. So that's why here you have 3.16 and minus 3, which is 0.6, divided by 2 will be 0.08. Anyway. So finally, tau max that you will get from this torque formula is 16 mt e by pi d cube, right? Because it is derived from that formula T by R is equal to G by G. Tau by, so if you remember the formula of tau max in terms of torque, so you see here this one. So here R will be d by 2, J will be forward moment of inertia, which is twice of pi d4 by 64. So we'll get 4 times pi d4 by 64. So 64 by 4 will be 16. So and T will be this MT E equivalent. So that's what we have written here. And this will be pi d cube. Okay, so finally you get 16 times 3.16 into 10 to the power 3 divided by pi d cube. So how much will you get? 16 into 3.16 into 1000 divided by pi. So you're getting 16.1 approximately. So 16.1 into 10 to the power 3 divided by d cube Newton per meter square. So we are finding the maximum shear stress and the principal stresses in terms of the diameter of the shaft. So now we can apply the theories that we have been asked to. First theory is maximum principal stress theory, then maximum shear stress theory, then maximum distortion energy theory that we have to apply. So first let's apply this maximum principal stress theory. So if we apply that, so sigma 1 will be equal to sigma y, and since sigma 1 we have derived that it was 31 into 10 to the power 3 divided by d cube. And if we convert, if we take d in mm, so um, so it should be multiplied with 10 to the power minus 9, right? What I have done essentially is now you will get, so d was in mm, so I have converted this into meters. So that should be d into 10, d is still in mm, but this whole quantity d cube into 10 to the power minus 9, that is in meters. Okay, so you get 480, right? And so from here, if you solve, you should get d somewhere around 40.12 mm. You can check the calculations. I'll have to just explain the procedure. Calculations you can do by yourself as well, but you should check the calculations. And you have then maximum shear stress theory. So maximum shear stress is given to you, and we have the formula for maximum shear stress in terms of diameter. So that should be equal to maximum shear stress should be equal to maximum shear strength. So our formula was 16.1 into 10 power 3 divided by again d cube into 10 power minus 9, which should be equal to 265. Because this 265 is in megapascal, so that is Newton per mm square. That's why we have converted this also into mm. Okay. And ideally, uh, actually, this will be this will be sufficient. Let me just see. I think 16.1 into 10 raised to the power 12 divided by 265. Raised to the power 3 and 3. Yeah, actually, ideally, you can find in SI units and then you can convert in mm maybe. So firstly, you find in SI units because this is in megapascal, so you can convert multiply this with 10 to the power 6, 480 into 10 to the power 6. So that will be in Pascal, Newton per mm square, and this is in 31 into 10 to the power 3. So that is moment. So that is in Newton meters, right? Um, So yeah, and this is in meter cube, so you get Newton per meter square. And now later on you can convert D into mm, so you should get somewhere around this. Okay. Similarly here also. These answers may not be exact, but you should get somewhere around these values, like plus minus 5 or plus minus 2, plus minus 3, like that. So it was 265 into 10 to the power 6. So you should get diameter here from maximum shear stress theory to be somewhere around 39 mm. Okay. And then you have distortion energy theory. So if you use that, you get sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So that should be equal to sigma y square. Now if you put all the values, so sigma 1 is how much? Still, so that is around 31 into 10 to the power 3 divided by d cube to the whole square, and sigma 2 is um, 0.8, right? 0.4, 0.08. No, so sigma 2 is 0.81, yeah. So 0.81. Okay, 6. So 0.8 approximately into 10 to the power 3 divided by d cube to the whole square minus sigma 1 sigma 2, so that will be 31 into 10 to the power 3 over d cube, and zero point 0.8 into minus should be plus or something. Sigma 2 is minus, right? So or not? Yeah, so sigma 2. Hmm. this minus this, then becomes this. Okay, so this is minus. So because second equivalent torque is negative, second equivalent bending moment is negative, this will be minus. So here it should be plus. Okay, and if this is plus, so you should get 28 into 10 to the power 3 divided by dq. So there's one more question. Anyway, so that should be equal to sigma y. So 480 into 10 to the power 6 to the whole square. Right? So if you solve, you can solve actually and just find the value of d. So this is you can find. So it's very easy. Just check the units. So Newton per meter square. So we just take d cube to the whole square other side. Okay, and this 4 into 10 to the power 6 to the whole square to the left hand side. So only unknown will be d cube and d cube to the power 6, and then whatever will be on the left hand side, you just do it raised to the power 1 by 6, so you'll get d. So let me go to problem number 3. Okay. So problem number 3 is you have a wall bracket with a rectangular cross section is shown in figure. I'll draw the figure. So wall bracket has a rectangular cross section. So the depth of the cross section is twice of its length. The force P is acting on the bracket at 60 degree to the vertical is one there. Force P acting on the bracket at 60 degree to the vertical is 5 kilonewton. And then you have the material. The material of the bracket is gray cast iron, which is having a yield stress of yield stress 200 MPa, and the factor of safety is 3.5. You have to determine the dimensions of the cross section of the bracket, and you have to assume maximum normal stress theory. Okay, so let me draw the bracket. So bracket looks somewhere like something like this. Um, it looks like this actually. Then here you have this cross section. Okay, and here you have thickness. So let's say I'm just saying the thickness is T and thickness. So this will be not in this plane, but it will be out of plane. So thickness of this bracket will be T, and this width is 2T. It's given that width is twice of the thickness, and let's the center line here of the bracket is this one. Let's say this is the center line of the bracket. Okay. Now you have a force acting on the bracket, which is 60 degree with the vertical. I'm sorry for the interruption. There is some electricity outage in my area. So maybe I'll have to stop this session here only. Um, or let's just wait a minute, okay? I can extend actually. Yeah, so let me start. Wait a minute. Okay, so here you have force which is acting here in this direction, which is P, which is 5 kilonewton, and it's making 60-degree angle with vertical. It's given in the question. So let's assume that um, this is point A, and this is x cross section. So cross section. I'm saying that this is the cross section that I'm focusing on, the critical cross section, and distance between these 2 points. So this distance is 300 mm, and this distance between the center line and the center line. So this distance is 150 mm. Okay, so obviously if this is P, so this will be P sine 60 degree, and this will be P cos 60 degree. So let me just do the solution. Before doing the solution, I just want to ask that at this point the bending moment will be due to this component of force also, that is horizontal component also, that will be P sine 60 degree multiplied by this 150 distance, that will be in minus z direction, and due to this also, that so the P cos 60 degree multiplied by 300. So there will be um, two contribution of bending moment from these two horizontal and vertical forces. Other than that, in the same direction. So other than that, there will be, so that bending moment will generate a normal stress at this point. Here maximum normal stress will be here. Other than that, this P sine 60 degree will generate axial force also here, because it is just like pulling. If you draw, uh, if you cut the cross section from here and you try to apply cut the cross section from here. Let's say we cut the cross section from here itself, okay, and we apply the moment. So the moment due to P cos 60 degree will be here somewhere. Um, I mean, there will be some bending moment, axial force here, and there will be some axial force due to this P sine 60 degree. So this axial force, when you draw the equilibrium free body diagram, will get translated here as well. And here there will be shear force as well due to this quantity here, and that will due to free body diagram that will be present here as well. But we are not interested in shear force because we have to apply maximum normal stress theory. So maximum normal stress that we will get at this point. So that shear stress, obviously, you can always take into account. You can draw more circle. At this point, you will have the shear stress due to this force, and normal stress due to this force and the bending. So if you, but that shear stress comes out to be very small. Reason is you will find that the thickness of the material will be, I mean, this 2T will be very less compared to 300. Let's see that. So P is 5 kilonewton, right? And SY yield strength that is given to you is 200 megapascal, and you have to take factor of safety as 3.5. which is given in the question, that you have to take a factor of safety of 3.5. So allowable yield stress or sigma max that can material can sustain, so that will be Sy divided by Fs, so that will be 200 divided by 3.5, which is, you can convert in Newton. So it is in megapascal, which is Newton per mm square. Okay. Okay. Now, now we already have a horizontal component of force and vertical component of force. Let's calculate that. So horizontal component, so I'm calling that as PH. So that is P sine 60 degree, and sine 60 degree, you know that it is root 3 by 2, so 5000 sine 60 degree, so that is root 3 by 2. So finally you should get 4330.13 Newton. And then you have vertical component, which is P vertical, so that is P cos 60 degree, that is 2500 Newton, because it will be half P by 2. So now we have bending moment at the section XX that we have drawn in the figure. Here you can see the figure. Okay, bending moment at section XX, so that is given by MB, which is PV into 300 plus P horizontal into 150. Finally, if you calculate, so this is 2500 into 300 plus 4330.13 times 150. So finally, if you calculate, so you will get 1399.52 into 10 power 3 Newton mm. Okay, mm, because this distance, this force is in Newton and this distance is in mm. We get Newton mm. So maximum normal stress due to bending, so that will be, this bending moment will be mvy by I, and y should be equal to t, because from the center line the topmost point is at a distance of t. So there should be 1399.52 into 10 power 3, that is Newton mm, into t, into I is 1 by 12 bh cube, because it is a rectangular cross section. So 12 I'm writing here, and b width is t, and height is 2t, so that will be cube of this. Okay, and this will be in Newton per mm square. And we are assuming that t is in mm. Okay, 2099.28 into 10 power 3 divided by t cube, that is Newton per mm square. So now we also have direct tensile stress. Component P horizontal is given by sigma t is equal to P by A, which is 4330.13, which is horizontal force that you have, and area is 2t square, right? So finally we get 2165107 divided by t square Newton per mm square. And there will obviously be shear stress at this point. It will not be purely there will not be purely normal stress at this point. There will be shear stress also, but that shear stress is due to this vertical force. So you can just write P cos 60 degree divided by the area, so you get average shear stress at this point. So uh, that um, that shear stress will be very small compared to this bending stress, and that's normal stress because bending moment usually introduces a large tensile stress at this point, and that again we have contribution from this axial tensile stress as well. So shear stress will be very small, so that's why we are neglecting it. Otherwise, if you want to include, so you have two stresses, sigma and tau, and then you draw a Mohr circle, and then from the Mohr circle or from the formula of principal stresses, if we have shear stress and normal stress, you find the principal stress from the formula of principal stresses, and if you have the principal stress, then equate that equal to the failure stress that you have, because we want to apply maximum. Oh, sorry. Yeah, yeah. Maximum normal stress theory is there or maximum principal stress? I think this will be maximum principal stress theory only. So yeah, um, yeah. So from there you can find maximum principal stress and equate it to maximum principal stress that is given to you. And now here, because shear stress, as I'm saying, you can calculate, but that will be negligible compared to normal stress. So we are assuming that only normal stress is there, and that we are taking as principal stress. So because if you draw more circles, so it will be something like this. You have a stress here and zero. I mean, let's say a very small shear stress, so the point will lie here, and large normal stress. So yes, the point will lie somewhere here. So and we are assuming that you have to draw this point here, and the stress is to this point here. You have to draw a radius, and then this using this radius you have to draw a Mohr circle. It will be something like this. But we are assuming that the contribution from shear stress is very small, so that's why this point, this radius will almost be equal to this radius. It means this point will lie here on the axis, and that's why this angle will become almost zero. So that's what we are assuming. Okay, so using maximum principal stress theory, that will be maximum normal stress actually. So sigma should be less than equal to sigma max, and sigma max will, sigma is sigma b plus sigma t. So due to bending and due to tensile force here, and that should be, let's say, I'm taking the limiting case, equating it to sigma max. So sigma b goes to 099.28 into 10 power 3 divided by t cube plus 2165.07 divided by t square, and that's equal to 57.14. So that will be a cubic equation, so we'll have to solve using calculator. So finally we'll get this. Is it t square or t? It is t square. So finally, if you solve this, so here you should get, here it should be free if you take t cube as a denominator. I mean LCM. So here it should be free of t cube. This should be t, and this should be t cube. So finally, we'll get t cube minus 37.89 t and minus 36,739.24 equal to 0. Okay, and if you solve this cubic equation using calculator, so finally we'll get 33.62 mm. that is your thickness. So we can go to the next part. We can go to problem number 4. So problem number 4 says that the shaft of an overhang crank subjected to a force P of 1 kilonewton and is shown in figure. I'll draw the figure. The shaft is made of plain carbon steel and the tensile yield strength is 380 Newton per mm square or megapascal. So the factor of safety is 2. Let me write completely. Is 2. What you have to determine? You have to determine the diameter of the shaft using maximum shear stress theory. So let me draw the diagram. So I'm drawing the diagram here. So let's say you have a shaft here. So shaft is originating from this section like this. Okay. And then you have here something like this, and then you have this cross section, and it is overhand shaft. So here you have something, and here you have its origin. So, oh, sorry. Okay. Now let me just. So now you have this. This has center. And okay, so these are 3 axes. This is y axis. This is z axis. This is, let's say, point A, and this is the cross section that you have. So there is something like this. Okay. Here also you have some cross section, and here this, let's say this is the center line at this point. And let's say here you have a force acting in downward direction, which is P, and the distance between the center point here and this force P. Let me just draw it. Okay, so the distance between the center point and this force P, so that I'm denoting with this color. So this distance, which is this is 500 mm, and the distance between the y-axis and this point, distance between y-axis and this point, so that is 250 mm. Okay, Let's, these all are in mm, so I'm just not writing the units. Now, so what you need to find, so at this cross, I'll take this cross section, okay, and try to find out the diameter of this shaft. So how can you find it out? So due to this force here, so there will be torsion that will be acting at this point, and there will be axial force that will be, and there will be shear force that will be acting, and there will be bending moment as well. So there will be three cases here. So this force here will introduce torsion. So torsion will be P into 500, and that will be transferred here, and this will introduce bending moment. So bending moment will be P into 250, because if you draw the free body diagram, so at this point this torsion will act in this direction, and then there will be a shear force in downward direction. When there's force in downward direction, that will introduce bending moment, and that bending moment will be P into 250, and then it will also introduce um, some shear force in this cross section. So in all these cases, as I said, that due to direct, so this force in transverse direction will introduce shear in the cross section. So we are neglecting that shear. You can say that we are kind of using Euler-Bernoulli beam theory, not the Timoshenko beam theory here. In the previous question as well, we have done that. So we'll take shear due to torsion, but we will neglect torsion. We will neglect shear due to the force, the transverse force that is acting here. We'll only take normal stress due to this transverse force at this cross section. So let me do that. So solution. So we have been given that, so factor of safety is 2, right, and P is 1 kilonewton, that is given to us, and yield strength is 380 Newton per mm square, right? So now we have to apply maximum shear stress theory, and we only have the information of this yield strength. So maximum shear stress will be, maximum shear strength will be yield strength divided by 2, because we have to rely on this data only. We don't have separate data for maximum shear strength of the material. So so SYS, so we just say that permissible shear stress so that will be SYE strength, shear strength, so that will be half of the yield strength. So half of yield strength will be 190 Newton per mm square, and now we have a factor of safety also. So the permissible shear stress, um, this is not permissible shear stress, but this is shear strength. Now we have permissible shear stress. So that will be SY is divided by factor of safety. So this is 190 divided by 2. So you have 95 Newton per mm square. Okay. Now the bending moment due to the moment due to bending, so that is P into 250, which is 250 divided by 1000, which is 250 into 10 to the power 3 Newton mm. Okay. And bending moment, moment due to torsion, torque, you can say, is a torque that is acting is 1000 into 500. So this is 500 newtons per 3 Newton mm. So bending stress due to this bending moment, so mby by I. This is the bending stress due to this bending moment. So 250 into 10 power 3, that is bending moment, and y will be d by 2, because that is the radius that you have to take maximum for maximum shear, for maximum normal stress. And then we have I as pi d4 divided by 64. So that is Newton per mm square. So finally, if you solve this, so it will come somewhere around to 546.48 into 10 power 3 divided by d cube, and then Newton per mm square. Okay, and then tau, shear stress due to torsion, will be mt into r divided by Coulomb moment of area. So that is 500 into 10 power 3, and here it is d by 2, and this is pi d4 by 32, right? So finally, what you will get is this also you will get 2546.48 into 10 power 3 divided by d cube, which is Newton per mm square. So you know that maximum tau. So you can draw a Mohr circle, and more maximum tau will be radius of the Mohr circle, that is sigma. So we have this sigma b, which can be taken as sigma x, and then that is sigma x by 2 to the whole square, um, plus tau xz to the whole square, because here we have sigma x in this direction and tau xz. This is actually x. Okay, and tau xz in this direction. Okay, so finally this will be your maximum shear stress. So let me draw the element. So here let's say this is a small element, so sigma x will be in this direction, and tau zx will look like this. This is tau xz. Similarly here also. Sorry, I think this. So this will be tau xz, and this will be tau zx. Okay. Now here we have sigma x is equal to sigma b. Okay, so this is, we already have the expression for sigma b, so I'm not writing here. And we have tau is equal to tau xz. So now if you put it in this expression, so finally you'll get tau max is equal to, and you have to use maximum shear strength theory only. So tau max you will get is 2546.48 divided by 2d cube, because here we have sigma x divided by 2 to the whole square, plus 2546.48 divided by d cube to the whole square and square root of that. Okay, so finally you should get 2847.05 into 10 power 3 over d cube, and you have to use maximum shear stress theory. So using maximum shear stress theory, so that so this should be equal to maximum shear stress, which is 95. So this unit is Newton per mm square, which is megapascal only. So if you solve this, you'll find d to be 31.06 mm. Okay, so finally it is. So this will be the final solution. So I will stop here for today. If you have any doubt, you can post in the YouTube comment window. Okay, so thank you all for your attention.